everyone, today we are going to look at air. All of us need air, right? If someone deprives you of air, you actually suffocate and you will actually die. Okay, that means that air is actually very important. Air that we breathe in is actually called oxygen, and that the one that we breathe out is carbon dioxide. When our cells carry out what we call chemical reactions or chemical processes, a gas that is often produces carbon dioxide. So that means that also if we don't let this carbon dioxide come out, we'll also land into health problems. So that means that air is actually very important, okay? But also again, if we take in contaminated air, which the one that can come as polluted air, will also get health problems. So that means that actually life has a lot to do with air. Okay, we could not be having life if we don't have the appropriate air, that is clean air. Okay, we will have a lot of things going wrong, ranging from the plants, ranging from going to living organisms, everything, microorganisms, those that live in water and things like that. That means that air is actually very, very important. So our interest in air, especially chemistry, is to know what makes up air and what makes up air by proportion. Okay, do we have a lot of particular gases and we have less of particular other gases? What is the percentage composition of air by volume? So those are things that we are going to look at in this presentation. So air is a mixture of gases, it's not a compound. This is still to basically still stress the fact that compounds are formed when you have elements combining chemically and forming what we call chemical bonds. For mixtures, for air, there is nothing like that. You have these different gases. These different gases are not combining with one another through chemical means. You just have them existing as a unit that we call air, but these gases are not combining one another through chemical means. So we say that air is actually a mixture and is not a compound. Okay? So there are very many results that we shall look at in our subsequent slide. As one, we actually call air a mixture, not a compound. But at least for now, let's understand this concept here, that the composition of air varies according to location and time. Okay? But for compounds, definitely, the compound, regardless of where you find that compound, it will always consist of the same elements and in the same fixed ratio. That is always something that I keep emphasizing. Fixed ratio, fixed proportion, regardless of where you get that compound. So for example, water will always be water, and it will always consist of hydrogen and water, regardless of where you find that water. But with air, the composition by proportion or by volume is actually different, depending on the time of the day, for example, or depending on the location. And I have two pictures to illustrate this quite well here. If you love what you call mountaineering or mountain climbing, as you go high up the mountain, the amount of oxygen actually reduces. So sometimes you get people getting, sometimes we call it mountain sickness. So people actually fall sick because of the fact that the oxygen that they get there is not very sufficient. So usually the body tries to compensate to make sure that you have more red blood cells to capture the little oxygen that you have there to maintain your life. And that is why athletes usually practice in high altitude areas or in mountainous areas, because there they're trying to acclimatize. That is to say, they're getting their bodies used to low oxygen concentration, and therefore more red blood cells are formed. And then when they come to the competition, they can actually perform better, and that's the reason as to why. Okay, so that means that if you're going to go for mountain climbing, you need to be aware of some of the health issues that can happen to you because of the issues to do with oxygen. And then we have divers. Divers are individuals who go underwater. Some can do it for purposes of leisure, others do it for purposes of basically scientific studies and discoveries. Okay, when you're inside water, the proportion of oxygen is actually low, and also you basically need to have the same oxygen just like what you have normally when you are not diving. So that's why we actually have this equipment around them to make sure that they can have sufficient oxygen when they are diving. Okay, so but generally in the atmospheric air, the largest gas by proportion in terms of volume is nitrogen. If we ask you that question, you should be able to say that. Okay, and then followed by carbon dioxide, oxygen. Oxygen has a percentage of 21%. Nitrogen has 78%. Carbon dioxide has 0.03%. And then we have what we call the noble gases, or the inert gases, helium, argon, and others. They form about 1%. Okay, and then we also have water vapor, which is constituted between, like we said, it varies between 0.5% to 4%. If you have humid, in humid areas, we have more water vapor than in, let us say, arid areas, the dry areas. Okay. So why do we say that air is a mixture? It's a mixture because actually the air is made up of these gases that are combined without having release heat or having to absorb heat. Okay, so there is no heat absorption or heat release. Just like also what happens with the most mixtures that we talked about, basically mixtures that we talked about, and then we also have the fact that to separate air into the individual gases, we can do that using what we call physical means. We don't need to use chemical means to do the separation. If you remember, we said that physical means, what you get is not different from the products, and the process is reversible. What you get can be returned to what you got it from. But for chemical means, what you get, you can't return to what it was through physical means. It has to be basically you form a new product. Okay, and for you to convert that new product again, it may have to be a series of other reactions that you can undergo to get what you got again. Okay, so that is the other thing. And then the properties of air. It's like the average properties of the gases that make up the air. Whereas we saw that with the compounds, for example, the properties of the new thing that you have formed, the new compound that you have formed, are not going to be the same as what made up that property, that compound. Okay? So what you make is totally new and to behave differently, to have different chemical properties. But for air as a mixture, what you have is the average properties of all the individual gases that make up air. Okay? And then the composition by proportion will always vary, and I've explained that quite well. So, but we say that with the compounds, the composition will never vary regardless of where you are. Okay, so we have two experiments that we are going to talk about, and the first one is determining the percentage of oxygen in air using copper. So this experiment is quite simple. What you have are two syringes. One syringe is empty. That means that it is not having air. And then another syringe is having air. Okay? And then inside here, you have a glass tube. And the glass tube is actually sealed at one end and at this end. Okay? And then you place, okay? So you put your copper tannings here inside the glass tube, and then you heat here. You heat the copper tannings there. So how will this process actually happen? This is basically a setup. Two syringes connected to a glass tube that is sealed at both ends using glass wool. Okay, and then you have about 100 mils of air here. You have 0 air there. You don't have, it is empty. I emphasize that. So you heat the copper tannings there. So how do you proceed with the experiment? What you basically do is that as you're heating here, you pass air over the copper tannings. Okay, and then keep, when you pass the air, it passes over the copper tannings, you're actually having a reaction. Okay, the copper is basically reacting with oxygen that is in the air that you're passing over it to form copper oxide. Okay, so part of the air is absorbed by that reaction. Okay, forming formation of what you call copper oxide. And then this air again that you have passed here, you push it back. You push this air back using this other empty syringe. And then you again push it. Okay, until you have black copper oxide here, until these copper tannings become black. Okay, so when they become black, means that you have now, that reaction has taken place. The oxygen has been used to react with that. Okay, what this also means is that what you will, where air that is going to be inside here is going to be less, because some of it has been used in the reaction here. Okay, that's something that you should know. So what will happen? The air inside the syringe will decrease by about this 21 cubic centimeters, and this is approximately 21% of the air. Okay, I've used this 21 for the reason that in our experiment we are using air of 100 cubic centimeters. If we use another volume of air, then we could not be using, we couldn't be expecting this 21 here. It could be something else. It could be another figure, but still that figure can bring us to about 21% of the oxygen that is being used for conversion of that copper. Okay, so that's why we have this formula here, which is 10 minus x over 10 times 100, basically converted into 100%. Where is this x coming from? That x is the decrease in volume that you have. It's basically the oxygen that you have used during the reaction. Okay, I hope that is quite clear. Okay, so basically that experiment proves that oxygen is actually used. The conclusion will be that oxygen is used during the process of reacting with the water. Okay, and the fact that we get about 21% proves that it's basically oxygen that we are talking about. Okay, so we move to the second experiment. This second experiment is still the same thing, determining the percentage of air. This time, the percentage of oxygen in air. This time you're going to use a burning candle. That is what you're going to use. So with the burning candle, you want to see? You can stand there. There, it's okay, you can stand there if you want to see. Or you want to see that. It is not there, it is here. You can see it. So the burning candle experiment can be used to determine the percentage of oxygen in air. So how do you do it? What you get a plastic lid, place it on water, and that water is basically contained in a trough. Okay, we got. So you place this lid here to basically support the candle that is burning. So what you do is get a measuring cylinder, or you can call it a gas jar. Cover this burning candle. This burning candle will continue to burn until a time t. Why will it continue to burn? Because what you have used to cover it will contain oxygen, and therefore it will continue to burn because the oxygen is still there. And when that oxygen is used up during that burning process, it will go off. The candle extinguishes, right? So when it extinguishes, you will notice that after it getting extinguished, you remove this jar and then insert a glowing splint into that jar. What you will see is that glowing splint will actually get extinguished. This is basically to mean that as the candle was burning, carbon dioxide was actually accumulating here. Okay, you have carbon dioxide accumulating there. So when you lower a glowing splint there, it will actually get extinguished to prove that there was carbon dioxide. So carbon dioxide as a product of combustion. So going back to our experiment, that is another conclusion that can be made. Going back to our experiment, because the oxygen is being used up here while this candle was burning, the level of oxygen, the level of water will actually rise here because oxygen is being used. So that means that the volume here decreases, and then it makes the water to rise, basically equalize the pressure in the tanks. Okay, so that rise will actually constitute to about 20 or 21%, which is basically something to do with oxygen having 21%, right? By volume. Okay, so that is the second experiment that you can have there. There are other experiments that we shall go with, that we shall deal with, for example, in rusting, for example, on carbon dioxide, and other experiments that we shall be looking at subsequently, especially in relation to conversion. Okay, so thank you.